Welcome to Proofs in Differential Calculus. My name is Roy Simpson. I'm a professor of mathematics at Kissimmee River College in Sacramento, California. In this proof, we're going to prove the product rule, which is for derivatives. Basically, the product rule states that if you have two differentiable functions, then the derivative of their product is equal to the derivative of the first function times the second plus the first function times the derivative of the second. And that's exactly what's written here. Now we're going to take a very geometric approach to this proof, and in fact it's a very traditional geometric approach to the proof. First of all, let's go ahead and I'm going to write in here proof here. We're going to let the function y equal f times g. And then what I'm going to do is I'm going to call this side length of this box, so it's a geometric proof, so you have to kind of visualize what's going on here. Side length of the box, we'll call that f, and the other side length here, we'll call that g, so that the area, when you multiply these two together, is going to be y, which is f times g. Now, the way the proof works is that we're going to wiggle the function g a little bit. We're going to basically try to get g to be a little bit bigger than it actually is. So I'm going to make a small box here. Now when we do this, notice that I'm just slightly changing the length of this long side that we called g before. And whenever you make a slight change in something, we often call that slight change a delta. So we denote that with a capital delta, and then that's a slight change in g. Obviously, this other length, this other side length is f, because that's the same length as what's up above. So if we want to find out the area of this blue square, it's going to be f times delta g. Just for notational purposes, I'm going to write it this way, delta g times f. And I'll try to keep the coloring on the letters the same. Why not? Not for any reason, I suppose. Now, that's all well and good, but let's go ahead and make a small change in f as well. And remember, whenever you're dealing with calculus, you're really dealing with infinitesimal, I can never say that word, but really small changes, right? So we've just taken this function g and we've changed it. So remember, g is just a set of outputs for a function, and we're changing those set of outputs slightly. Well, here's a function f, and I'm going to say, well, what if we were to have a slight change in those outputs? Okay. Graphically, in other words, in this kind of box that we're building, the area is going to be delta f times g. So let me write that in. That's a delta f times, and then I'll use again blue for g, just because I'm using that blue. Well, that's not blue, that's a red. So let me try blue again. All right. Now what's interesting is the rest of this square down here, the stuff we didn't put in. I'm going to put a green box in there. And as you could probably guess already, that the area of that box is just going to be delta f, change in f, times change in g. Okay, and this is what we need to visualize for our proof, is that we have a function. With both of these functions, in fact, we're just wiggling their outputs by very little, and then you get this box here, and we're going to use the geometry of this box to help us with this proof. Now I want you to note something. If f times g was this black box here, and then we have this change that's happened, so we want this change in the product of f times g. Well, here the black box is just f times g, but really the change in the product of f and g is all this other stuff we had to add on to it. In other words, if we wiggle f and we wiggle g a little bit, the change is going to be that red box, that blue box, and that green box. It's incredibly important that you understand what I'm saying when I say that a change in our function output here. Our original function again was just f times g, and now what we did is we wiggled f a little bit, we made it a little bit larger, we made g possibly a little bit larger. Okay, So the change in the product is no longer the black box. It's now this bigger, big box, which is basically the sum of all these boxes, okay? So the change that we did in the product is just the red plus the blue plus the green. I'm sorry I have to say that at least several times. So here we go. I'll just say the change is delta F times G plus delta F times delta G plus delta G times F. That's just the areas of those boxes. Now, if we're talking derivatives here, that means that eventually we're going to have like a dy dx or something like that, right? We're going to have, our goal is to have a dx on the bottom. So why don't we introduce that dx right now? Let's go ahead and divide both sides by delta x. Divide both sides. Again, it's incredibly important that you're following what I'm doing here. So I divided both sides by this little delta x, and the reason why is because if you look back at our claim to fame here, we're claiming that if f and g are both differentiable functions, then dx of f times g, in other words, delta over delta x of f times g. Dx is a fancy, well, it's a calculus way of saying that our deltas, our change in, is becoming incredibly small. Capital delta is reserved for finite changes. D's, lowercase d's, are reserved for infinitesimally small changes. So this is why I've done so much work so far to get to where I have a delta over delta x, and then I have f times g. So you can see what I'm trying to do. I'm trying to rebuild or get to what we want to prove. But I need these deltas to get really, really dinky. So let's go ahead and do that actually. Let's talk about how we can make those really, really small. Let me put in a dividing line here so that I can do the rest of my proof on the other side. So I want to know what dx of f times g is. Well, by the definition of the derivative, this is just the limit as the change in x goes to 0 of, well, our change in our function value, so our change in f times g, over our change in x. That's what we want to, that's what the derivative is defined to be. It's just defined to be, well, as we let x, the delta x, get really small, obviously the change in our function value also will get pretty small, hopefully. Well, let's exchange that delta f times g over delta x for what we've expanded it out to be here. So this is the same thing as saying the limit as delta x approaches 0, and I'll just go ahead and copy and paste that here. Now we're going to go ahead and split this limit. Now I'll have to make an exception in a moment, but I'm going to go ahead and split this limit right now. And remember, you can only split a limit if each of the individual limits that you're splitting it into exist. So that's a very important point to make. But we'll find out that each of these limits does exist. So splitting this into the limit as delta x approaches 0 of delta f over delta x times g plus the limit as delta x approaches 0 of the next product, right? Delta f times delta g over delta x. And again, I'm just hoping that these limits exist. If they don't exist, I will not be able to continue with this proof. Plus, and I have a feeling you won't be able to see, so I'm going to have to kind of put the plus down here actually. So let me erase my last plus over there. Plus the limit as delta x approaches 0 of our delta g over delta x times f. Alright, now I'm going to make a little side note here because there is something kind of important to note. The first thing I want to note is that G and F are not dependent upon delta x. So do not depend on a slight wiggle in x. Remember, these things, G gets an x plugged into it, F gets an x plugged into it. The stuff that gets more than an x plugged into it are things like delta f. Delta f happens to be a slight change in my function value. It's going to be my function evaluated x plus a delta x minus my function value. If you think about this, this is basically saying, listen, I have my function that's evaluated at 2, and I want to see what happens if I evaluate at 2.1. So in that case, my delta x is going to be at 0.1. In fact, maybe I should be writing this down on a separate sheet so you can see what I'm talking about. So, like I said, for an example, you have f being evaluated at 2, and what you want to do is you want to find out what is f evaluated at 2.1. The change in the function value between these 2 points is not 2.1 minus 2, okay? Because those are what you're inputting, 2.1 and 2. The change in the function value is f at 2.1 minus f at 2. That's how the function changed over that interval. Well, if you think about it, that's like saying f of 2 plus 0.1 minus f of 2. We wiggled, our little delta x was a wiggle of 0.1. So our change in output is just the difference between these output values. That's what I was saying in the previous slide. So let me go back to the previous slide here. The change in the function output, as you see in green down here, is just the difference in the function values between the new function value and the old function value. Same thing about the change in the value of g. It's just the difference between the new function value and the old function value. That is important for me to say because when I look at these limits, this one right here has a product of two different functions, right? Well, we're letting delta x approach 0, and we just see right down here, delta f relies upon delta x. So I have to keep this delta f inside this limit. However, g itself is just g of x. It's not g of delta x, it's g of x. There's no delta x inside g, and there's no delta x inside f either. So no delta x here, and there's no delta x inside there. That's what's very important to note. So I can basically pull those two functions out front. I can pull this g out in front of this limit, and I can pull this f out in front of this limit. What else is very important is that now that I know what delta f and delta g kind of look like, I could say, well, this limit right here, is this middle limit as delta x approaches 0, I could split it into the limit as delta x approaches 0 of delta f times the limit as delta x approaches 0 of delta g over delta x. So let's do this all in one fell swoop. Now all I did right here is I just rewrote what we had before so I can have a nice clean base to start from. Now because again, g doesn't rely upon delta x, I can pull that g out front. So that's g times the limit as delta x approaches 0 of delta f over delta x, which is very special actually. This one right here, I'm going to split this limit. Again, I'm hoping that this split, both of these limits will exist, because then it will justify me being able to split it. If one of these doesn't exist, then I'll have to go back a step, go back to basically go back a single step and rework the problem. And then finally, this last term down here, that f, function f, does not rely upon delta x. So I'll just pull that function f out. And we get this beautiful result here, which may not look so beautiful yet. However, the limit, the first one here, the limit as delta x approaches 0 of change in output over change in input, that's the definition of a derivative. That's the prime definition of a derivative. That's g just times dx of f plus, I'm going to skip that middle part and walk over here, plus f times, well, this last term here, the limit as delta x approaches 0 of the change in output over change in input. That again is the definition of derivative. So that will be d dx of g. Now if you look at this, this is almost what we wanted to prove. We wanted to prove that d dx, or the derivative with respect to x of the product of f and g, is a derivative of f times g plus f times the derivative of g. And we have so far the derivative of f times g plus f times the derivative of g. It's this stuff in the center that we're concerned with. Well, if you look back a slide here, we want to know what happens to delta f as delta x approaches 0. That's an extra slide here. Well, here's delta f. Let me highlight it down here. Here we are. And as delta x approaches 0, delta f turns into f of x minus f of x. Let me write that down so you can see that. The limit as delta x approaches 0 of delta f is going to be the limit as delta x approaches 0 of f of x plus delta x minus f of x. Well, if delta x is approaching 0, that's going to be f of x minus f of x, which will equal 0. What does that mean in our proof? It means that this business in the center is going to approach 0 times, and then again, this is just the derivative with respect to x of g. And as we mentioned in the beginning, this is a very important point to make, because I said I can only split these limits if these, I can only split the major limit, the first limit that we were dealing with. Let me hop back here. This first limit right here, okay, I said we can only split that up if what we split it into exists. Well, one of the things that you have to assume with this proof is that f and g are both differentiable. They told me f and g are both differentiable. That means that, let me hop down here. That means that this limit, the first one, which is the limit as delta x approaches 0 of d delta f over delta x. Let me find my cursor. It's hard to see on here sometimes. Anyway, this limit is just the derivative of f, which they told me existed. The last one over here, this one right here, is a derivative of g, which they told me existed. This one right here is derivative of g, which they told me existed. And this one we've shown is just 0. So all these limits do exist. So this just turns into a nice, beautiful g times d dx of f plus f times d dx of g. That is the proof. We are done. QED means that we have completely proven this. There's nothing, no holes in our proof. And that is a really nice proof using a geometric background.